Hello everyone, I'm Victoria and welcome to Yukaria Code. Today we're going to be solving Leetcode 797, all paths from source to target. And so it says, given a directed acyclic graph, a DAG, of n nodes labeled from 0 to n-1, find all possible paths from node 0 to node n-1 and return them in any order. The graph is given as follows. Graph I is a list of all nodes you can visit from node I. That is, there is a directed edge from node I to node graph ij. And then they show us a visual of it and input. And let's just go through that real quick. So in our picture here, it corresponds to our input graph, where we have a list of lists, and each node is an index. So node 0 is that list, node 1 is that list, node 2 is that list, and node 3 is that list. So again, they said from 0 to n-1 is our graph, and they weren't kidding. And so with this data structure input here says, for node 0, we're connected to 1 and 2. So in our image, node 0 goes to 1, node 0 goes to 2. And then it also says that node 1 goes to 3. So node 1 goes to 3. And node 2 goes to 3. And finally, 3 goes to nothing. It is the ending node. So that's all well and good. And the problem wants us to find all paths where we start at 0 and we make it to 3. And just from the visual here, we see 2 paths, but can we do that algorithmically is the question. And well, we wouldn't be solving a Leetcode problem if that were not the case. So let's dig into the code here and see what we can make happen. So one way to start this off is to have a good idea of where we want to end. So in a graph of 0 to n-1, that means the end is going to be the length of the graph minus 1. And since there are going to be multiple paths potentially, we're going to have a list that will assign to res that will ultimately return. But we want to build up paths. And we know that we're starting from the 0 node. So we can start our paths with as a list with one value 0 in there. And we'll do this in a depth first manner. So let's define a function dfs, and that'll take node, which will correspond to the integer value. And we know, now let's think of a base case. We know we've hit our winning condition when we've gotten to the point where if node is equal to n, then what we can do is res.append a copy of paths. So whatever we built up in paths, as we got up to the end, that's what we can return. But then you might be thinking, well, how the heck did I get there in the first place? And so let's get to the recursive part of it and the crux of the problem here. So this is going to be backtracking. We're going to be checking whether a depth first search from each adjacent node given from the starting node in our call, whether it leads to the path. So we'll do for adjacent in graph node. So like we showed in the beginning, where in graph of 0 we had a list of 1 and 2, we're basically visiting each of its neighbors. So what we can do is say, okay, we're visiting that, so path.append adjacent, and then we want to do a depth first search from adjacent. And when we're done with that, path.pop, maybe that had a success condition in there, maybe it didn't. Either way, we got to clean up our function for the next call. But if it did, it'll record it in result, making a copy of paths, and update that for us. And if not, well, so be it. That's life. And that looks simple. Computationally intensive doing something like that because you have to make a decision in each part and check it. But let's try that starting from DFS on 0 and then return result. Let's see what we get. Wrong answer. Okay, yeah, so I have my variables named a little wrong here, so let's fix this up. Path, that looked named incorrectly. Yeah, so assuming you name your variables in a consistent manner and call them so, this looks like this works. Where all paths start from 0. Depth first search, check if we hit the end. If we do, we append to result a copy of that path. But otherwise, we recursively check whether we reach that end based on the neighbors at each position in our depth first traversal. Then return our result, and let's confirm with a complete submission. And yeah, there we go. Nice. Hope that helps someone out there. Have a good one.